Welcome to Embedded. I'm Alicia White, alongside Christopher White. Today we are going to talk more about robots. Soft ones this time. Soft-bodied robots mean squishy robots. You know what else is squishy? Gummy bears. And no, actually, I haven't lost my mind any more than usual, but our guest is Kari Love, and she's making soft-bodied candy robots and spacesuits. I'm sure it will all make sense.
I'm confused already. Hi, Kari. Welcome.
Hi, don't worry. I'm confused too. I still haven't decided what I'm going to be when I grow up, and that's how you end up with these combinations.
I understand that, and yet we didn't even mention costume designer and puppet maker. Those are all coming later, so there'll be more. Before we get there, could you introduce yourself like you would if you were, attending a SuperCon panel for Hackaday?
Sure. So I'm Kari Love, and I am one of the two collaborators at Super Releaser, a soft robotics consultancy. When we say soft robotics, people often get really focused on soft actuation, and it is one of our primary areas of interest. But really, we ask people a broader question, which is, have you considered a soft part? Because sometimes you don't need to make an entirely soft system in order to have compliance in a physical sense, make a lot of improvements to your hardware. So we want to consult with people and find out whether or not we can add items or workflows that will create more robust, more simple, more novel ways to approach your prototype. The other things that I do are that I teach soft robotics at NYU's ITP program as an adjunct professor, and I work wardrobe on Broadway. Right now I'm working at Amelie, which is a new show that's opening, and I also have worked in spacesuits in the past as a NASA contractor. I am a partial owner of Final Frontier Design. I own a very small percentage of that. And then I also have worked in puppet building. And as a puppet builder, I've had the pleasure of working at a lot of different places, including the Jim Henson Company.
Well, we could just talk about that for 6 hours.
I know. Oh, my goodness.
So I know you have an agenda, and I'm going to ruin it.
No, it's fine. Go ahead.
So soft robotics is an interesting term, and it's one that I don't know that many people are aware of. So can you give like a 30-second?
Well, doesn't everybody just skip to the robot in Big Hero 6, the super AI, the artificial intelligence, and he's giant and he's very squishy?
I think the thing that's interesting for me about Baymax and being part of the soft robotics conversation is that, one, not as many people saw that movie as should have.
No, it was a great movie.
Really, really wonderful. But the other thing is, I think that people don't realize that Baymax was inspired by a real robot. That the team that was working on the creative development for that movie wanted to take inspiration from real world robots. So they went to different labs all over the country. I don't know if they extended to labs all over the world even. And Baymax was inspired by the work of Chris Atkinson at CMU, that he was working on the idea of soft-bodied robots for healthcare. And that really captured their imagination. But there are also other robotics ideas that are in Big Hero 6 as well that they're working on at that institute that are inspired by other sorts of real-world robots. So I think that when introducing the idea of soft robots, they may have seen that, but they didn't really take it out of the fantasy space.
Okay, so if we do take it out of the fantasy space, what do we get?
That is a very fun question. And the reason why it's a little daunting at times to even define what this is that there's a really broad spectrum. So things like Baymax are inflatables. There are lots of pneumatic soft robots. There are lots of hydraulic robots. They are maybe made out of silicone, or they're made out of heat-sealed fabric, or there's ones that are made out of paper that are pneumatic and self-folding and origami. But there's this whole other side of what's called the field of soft robotics that's in the biospace. So there are things that are made out of rat heart cells that are actuated inside their own power source, which is some kind of glucose. Or there is a very, very broad field of what soft robotics is. There's theoretical computational robots that are only predictive of soft behavior pixels that don't exist in the real world, and that those are also soft robotics problems. So it really is just, if you are trying to engineer softness into a complex integrated system that would utilize some computer control, that's usually what soft robotics is. But there's all of these kind of fuzzy spaces in between. And a lot of it is very interdisciplinary. So you'll have chemists working with biologists, working with people who are electrical engineers, and you're coming up with these bridging sort of systems and bridging problems. Did that make more questions than answers?
Oh my God, so many questions. Soft robotics pixels.
Pickles?
No, robotic pixels.
What is that? I mean, is this a display? And yeah, what is it?
So that particular work is being done by an integrated team. I would actually have to look up. I know part of the team is at Columbia University, but I don't know if there are collaborators at other spaces. It's a Voxel based pixelated robot system where they have essentially their blocks, like little Lego blocks, digital Lego blocks, and they have been assigned different physical behaviors that it moves at some times. It has a certain amount of compliance or elasticity, and then that different ones actuate in different times and different patterns. But a lot of the work in that is about evolution. So in an example, maybe you start with a cube, and then you have the computer auto-generate different forms, like different areas of softness and different areas and different patterns when each part actuates. And then they're given parameters. So the goal is for it to get from one end of the screen to the other end of the screen as quickly as possible. And then it becomes an AI problem where they just run as many variations as possible. And they evolve over time to become more and more complex and being able to solve the problem more efficiently. They're really interesting.
Yes, they are. I'm not sure I got all of that, but I wanted to actually go on anyway. Whenever you say compliance, you mean squishiness, softness, we talk some about regulatory compliance, and that's totally different.
Yes. And actually, it's kind of something that I struggle with a lot talking about soft robotics, because a lot of the words that you would want to use to describe soft things are already taken by other fields. So you say soft and people jump to software. You say flexible and they're like, oh, flexible systems. Or you say compliance and they think regulatory compliance. I really do struggle with finding words that aren't loaded with other meaning in different domains. When I talk about softness, there's kind of several different factors that I point out to people when you're talking about material softness. So there's the flexibility of the material. So if you think of some thin plastics or even thin metals, fabrics, those things are flexible. You also then have the durometer, which is like what I would call like the squishiness factor, like how hard is this thing versus how much does it compress? And then there's also elasticity. So does it elongate? Does it stretch? And that these components that we would all call soft embody different physical characteristics and possibilities, and that you can have things that are one of these three and not the others. So you can have something that is. Yeah, so you can have something that has a squishy durometer, is flexible and elongates and is elastic. So, or you can just have one. And then, so that changes the complexity of your problem and your solutions.
Well, you definitely have terminology problems, because the word soft has like a whole bunch of different antonyms. It can be hard, it can be rough. And so you have to distinguish. I mean, you didn't even mention, is it plushy? Is it physically soft, like fur, or is it sandpapery? And that probably doesn't work so much in soft robotics, but if you were building something medical, you might want it to be non-slip for prosthetics, or maybe you want it to be soft like a plushy animal that you can snuggle with. And so you do have even more terminology. Yeah. But let's go on to soft actuation. I had this idea that I would explain octopus physiology, given my very limited understanding of it, and you would tell me if it's the same model you would use for soft robotics. Does that work for you, or do you want to describe it from like first principles and not involve cephalopods?
Well, I always want to involve cephalopods whenever possible, but I did think about whether or not that would be illustrative for the particular problem space, and you end up against this like very unsatisfactory answer, which is it depends. And I think the "it depends" in this space is kind of interesting to me too, because there's this idea where a lot of roboticists were really interested into biomimetics. So actually mimicking nature. Yes. And so there was a lot of effort, and there's still a lot of effort being put into directly copying systems from nature. But there has also been kind of the growth of the idea of the bio-inspired design. So you're not trying to like slavishly reproduce what exists in nature. Instead, you're taking principles from nature and trying to extrapolate that into something that's simple and usable and applicable to a particular problem. So if you tell me how a cephalopod moves, I can say, yes, you could create a soft system that mimicked all of those things. But probably what is going to be more functional is to take some bounding around that and say, what would get me a more simple solution than the exact copy?
Oh, yeah, because they're complicated. They've had millions, billions of years to get it right for their situation. I don't have a good mental model of even how you would start soft robotics. I mean, all of mine go back to putting air around encapsulated air, putting an air-filled balloon around a hard skeleton, which is not what soft robotics is really about. So where do I start? Where do I even get the concept of what we mean?
Let's see. So we're going to narrow down a bit. So like I said, we're starting at a field that's so big that it could be made out of like literal biological cells, or It could be just a chemical system and not involve any kind of traditional engineering solutions. Let's say we're going to just talk about pneumatics and have an inflatable robot. In this system, it ends up being that it depends how complex what you want it to do is. And then the way most people go about solving these problems are through direct prototyping. You have some concept by observing something in nature or having built something before where you know that has a property. One of my favorite like simple soft actuators is just two pieces of airtight film, and then you cut them into a spiral that has volume, and then you weld the edges together, and then as you blow it up, what happens is when it's not filled with air and you hold the top, the whole thing just hangs down, and you have like kind of a wavy sort of piece tubing essentially. But as you blow it up, it becomes more stiff. And as it becomes more stiff, it goes back to its original flat shape before gravity worked on it, and it pulls itself up. The spiral tightens and pulls up through the air, and by going through that motion, it lifts itself the distance back to where the air supply is coming from. The way in which I predicted this would move had a lot to do with understanding how spirals work in fabric and then extrapolating like how inflatables work. There is more of a movement now to be able to computer model these things, but we're in the part of the understanding loop where the heaviest lifting is done is in the iterating process, the physical iteration. So you build and test and build and test and build and test. And then once you have something that does something interesting, then maybe you want to model that. And maybe you turn that into a design principle that then you turn to an application. Does that make sense as a process or a way to understand the problem space? It's actually really hard without
visuals. I'm so happy this is a podcast.
Common problem.
I guess that the process makes sense, but I got lost in imagining spirals, and I think maybe I want to go back to that because it was important. So I cut out something that looks like a spiral, and I end up with a balloon that when it's flat, it's in a spiral shape. When it's unfilled, I guess.
When it's sitting on a table, it looks like a spiral shape.
Okay. And then I put air into it, and the air makes it go flat.
So right now, let's start where a place where you're visualizing it's when it's sitting on the table, your balloon is a spiral.
Okay.
But when then you take one end and you lift it up off the table, you just have a long dangly tendril.
It is no longer a spiral. It's just there.
A pigtail.
You can't see that it's a spiral.
Oh,
it's just like a wavy looking tail.
Okay.
Now, as you inflate it, the air pressure causes it to stiffen. And as it does, the stiffness makes it want to return to that spiral shape. And as it's going against gravity, it's pulling itself up and up and up closer to the air supply until it's a flat spiral suspended in air. It's now a flat sheet again.
So the air supply is at the top.
Okay. And so we start out with something that looks sort of like a line-ish like thing. And as it gets more air, it becomes more spring-like until at the top, it is now a coiled spring, flat spiral. Okay.
Yes.
And because it is this shape, we can use it like we might use a spring.
Yes. Now you can, exactly. Now that you know what it does, you can apply it to a problem.
And you can change the spring constant depending on how much air you have. And that actually now gives you a whole realm of possibilities.
Exactly.
Okay. I'm in for that. I got it.
So now kind of to take another kind of a more classical shape. I started with one of my favorite shapes, and also I like working with heat-sealed materials. So like it's a realm I enjoy. But kind of a very classical soft robotics problem is the idea of like a gripper. A silicone gripper is a very, very popular sort of soft robot.
Well, yeah, because there's so many applications. You think about fruit and being able to move fruit from one spot to another, or grip. I mean, even holding hands or, yes, okay. I'm on board with grippers. Might have called it a claw, but a gripper is a better word.
Yes. So a soft robotic gripper is like a very, very popular problem space. It's something that people are trying to commercialize, and you'll see lots and lots of versions of them across soft robotics. And there's various ways in which you can solve that, even within that problem space. It's kind of wonderful thing about soft robotics is like there's a million ways to solve the exact same problem. I think it's probably true of every element and every domain of engineering that's true. But I think because soft robotics is so new and everything feels novel, like any variation feels like totally different. But in those particular systems, a lot of them are relying on the elasticity of something like silicone. So in those systems, you fill them up with air. Oh, we should start with a classical model. Let me start again. So a very classic soft part is a Mckibben muscle. I assume you're familiar with Mckibben muscles?
Nope.
Would you like me to cover what they are? Okay. Mckibben muscles are a kind of pneumatic system that was invented in the 1950s. And by a guy named Mckibben, surprisingly enough, who wanted to apply them to prostheses. And they are a air bladder that is then covered with a kind of woven fabric or some kind of other structure on the outside, that as the tube inside inflates, as it grows in cross-section, the weave causes the piece to shorten in length.
Inchworm.
Yes, and so that's how you get it to do work. And so, like, this is a very, again, a very classic soft system. And they're applied all over the place. So the ways that you are dealing with that system is that you're causing something to constrain the elastic material, and that is changing the performance. You can do the same thing by constraining just one side more than the other side, or you can constrain in strips around it, which creates ribs. And by doing that, you can then make bending actuators.
Because you are putting pressure on one side differently than another.
Yes, and then the uneven inflation allows it to bend.
Okay. Yeah, I can get that. When I was preparing with the octopus, I had this idea of talking about partially filled water balloons, the long ones, and then you put it in a little bit of water, but you don't put any air in, and you can push it. And when you push the long, so you have the long part, and you push it on the shorter. You have a hot dog shape, and you push it in the middle of the hot dog. Because it's a water balloon, it just squishes out. The ends don't really move much. And what you're saying is, if you squish it a lot in the middle, you hold the hot dog in the middle. Chris's head is in his hands because he hates when I do this. But you're squishing a lot on the water balloon, and the ends have to get further apart. When you squish in the middle, they get further apart. When you release, then they get closer together. Am I building the right mental models, or should I be really thinking about air? Water's a little easier for me.
I think we should move on from the specifics because it's very difficult to.
The specifics, I think, are probably our problem here, because the mental models you're building are correct. And actually, what you've just switched to is that you like to think about hydraulics more than you like to think about pneumatics. And that's perfectly reasonable. Like, you can touch water. It's a little easier to get your head around. I think the thing that is the truth about this conversation we're having is that the way you understand how these soft systems work is actually that you observe them. You observe them in nature, or you observe them in the laboratory or in your garage. Like, that's how people are coming to understanding about soft systems.
Are there YouTube videos that, or maybe you can recommend a book or something?
Oh, yes. Watching YouTube videos of soft robots is a wonderful rabbit hole, and people should totally go down that.
Okay, I'll get a list of some of the ones you like best after the show. We'll put it in the show notes.
Excellent. Yes, I think that when you're building these mental models about soft robots, yes, the answer is if you have seen a soft system, and a soft system can be something as simple as a water balloon, then yes, that is how you're coming to understanding about how different materials work under different amounts of pressure. And the thing that's interesting to me about the water balloon example is that so in that one, you're dealing with, again, something that's flexible and something that is elastic.
Yes.
And as you deal with elastic systems, a lot of that starts to depend on the thickness of the walls. That if you have a thicker wall of something that's elastic, it's a lot more stable. And if it's thinner wall, it will distort more.
Sure.
So like the complexity mounts very quickly.
Well, I mean, I see why more thickness would add less elasticity. But why does that make it more complex? That just seems like a constant in the system. You have to figure out how much force to use or how much resilience to breakage you have.
So it's not that it's thicker is more complex. It's that if you have a gradient of thick and thin.
Oh, inconsistency in manufacturing is always complex. Yes. Okay.
Oh, not consistency. Intentional. It's a design parameter.
Oh. Yes, because you want to be able to be flexible over here, but not over there.
Yes.
Yes, like my neck wants to be flexible, but my cranium does not. Okay.
Yes.
Christopher's head is no longer in his hands, but he still looks doubtful.
Christopher, what are you doubtful about?
Nothing. I'm just enjoying listening to.
Should we talk more about actuators and different types, or should we go on and talk about candy?
I feel like if we spend a lot of time on actuators, it's just going to be confusing.
Well, maybe we could talk
the visual.
Maybe we could talk a bit about building them up into more complex systems, because maybe describing some of the systems you can build out of actuators might be.
Well, now we have an inchworm and a spiral spring.
Right. What do I do with those?
Well, the inchworm can walk. The spiral spring can spring. We can build Tigger from here. Sorry. Go ahead, Kari.
So let's talk about why you would want a soft robot.
Yes, thank you. That's where I'm trying to get to.
Okay, great. Let's talk. So there are lots of reasons you'd want a soft robot, and then there are some downsides why people don't want soft robots. So we can talk about both. So people want soft robots because we would like to be able to collaborate with robots. So we would like them to, for one, we would like to be able to wear them on our bodies. We'd like to be able to do that because there's medical utility maybe from it, things like gait training robots. You may want to wear a robot because you want to be stronger or faster. And that once you put a human in a hard robot system, there are many reasons why that might be suboptimal. So one is the human factors. Like humans are soft and hard together. We are not hard systems ourselves. And when you try to put us in hard systems, we are uncomfortable. We can be injured by it or injure ourselves with it. And also, you end up with this mass versus power problem. Like you have to have a power supply that is so large in order to move the massive hard robot that then you're losing the gains that you're trying to get. So another one advantage of soft robots is the one that you talked about, which was like when we talked about grippers, we're talking about fruit. So fruit is a wonderful problem space to think about because one, fruit is soft. It needs to be handled delicately. And the other is that fruit is irregular. There are no two fruits that are exactly the same. And so traditional hard robots try to overcome these kinds of problems with very robust sensing, but that sometimes you can get around some of that complexity by actually making this physical system soft. You can have more flexible applications and handle a wider variety of materials. One of the popular ideas of why you would want a soft robotic gripper would be kind of these new large warehouse systems where you're packing all kinds of dissimilar items. So how do you get a robot that can handle all of those differences? Another reason would be environmental constraints. So the Navy is very interested in soft robots because there are all of these very, very successful biological systems in sea life. The majority of sea life is either all soft or soft and semi-soft, like fish tend towards cartilage rather than hard bone. And so there aren't a lot of hard moving systems. So when you start looking at things like submarines, there's some feeling that they have already reached the limit of how successful they can be in these hard-shelled vessels. So they may be able to have a lot of advancements in terms of speed or stealth or ability to use sonar in some ranges where they can't use sonar now if they were able to switch to a soft system. Why else would you want?
I cannot wait to drive my personal jellyfish.
Me too. That sounds really amazing. And then also space. So I'm interested in space problems and have worked on space problems before. And so when you're dealing with space or undersea or like in a volcano, wherever these like extreme environments are, you suddenly have other kinds of problems. So for example, in in a spaceship, you're not just limited by how much weight you can put up because the fuel is very expensive, but you're also limited by the stowage space. So you often want to build something that's a lot bigger than something that you can launch. So by adding kind of soft or flexible components, maybe that you can pack these things much more efficiently and then be able to deploy them.
Okay. I think that all makes sense. One question that comes to mind to me is, why didn't we start this way? It seems like mimicking nature is our natural way to kind of figure out how to make devices and other things that act the way we want them to. It seems like we would have started with soft robotics instead of gears and metal. Was it just a materials issue historically, probably?
I think it's a predictability issue.
Okay.
So the complexity of these soft systems is the thing that's one of the cons. So they're nonlinear systems. So that's what people always say. It's a nonlinear system. So that means that we can't model it under our current understanding of physical modeling or computer modeling. So it is much more dependent from things like manufacturing error. So variations and consistency become a big hurdle in terms of these kinds of behaviors. And then I think that also there's the durability issue. So a lot of the soft materials that we have had are really averse to friction, like wear from friction or puncture or kind of all of these normal day-to-day hazards that things will be running up against.
I mean, that makes sense. I mean, if I go back to my water balloon example, there are many things that go wrong pretty easily with that. And of course, pneumatics have the same problem, that you don't even know that there's a problem sometimes, depending on what state you're already in. But you mentioned mass in wearing hard robotics. How does a pneumatic system make that lighter? I always think of air generating pneumatics as relatively heavy and expensive power-wise.
Yes, and I think that is one of the arguments against the current. So I think that there are some systems right now where it is a pneumatic system where they're putting on people's bodies. But then in that case, even though the pneumatic system to generate the air is heavy, you can switch to things like compressed air so that you're not generating the air as you go. And so you could switch to that, and then you'd have some way where you'd switch out the cartridges. But the thing is that even though it is heavy and power inefficient to create the air, you do still need less power than you do for an equivalent hard system that's heavy. Some of the systems that are wearables are actually like a more cable driven. So they're like spooling up cables to pull them along the body. And those ones I think are pretty interesting to me because you're using the hardness of the existing bone structure of the human to provide the predictability, unlike the hard components to anchor against.
Yeah, okay. Cabled things, I always immediately wanted to lose my cables because, frankly, I lose my cables. With pneumatics, if you're cabled to, I mean, I guess if you're cabled to a space station, then that's one thing. But I want to, if I have an exoskeleton that is helping me with fixing my gait so that I don't walk so that I damage my knees, or something on that order, that's something I want to be able to walk on different surfaces and try out in different places. So I think we need to figure out how to put the pneumatics on the person. But what you said was important. Compressed air is a thing, and you don't necessarily lose it in these systems. You don't need to generate compressed air. You just need to pull it from one place to another. Is that right?
Yeah.
Yeah.
Well, it depends how leaky your system is, intentionally or unintentionally. Like you can build leak into the system as part of the operating parameters, or you can try to make a less leaky system so you can keep the air and move the air over different amounts of time. But I think that when we're thinking about soft robotics right now, I think it's often helpful to think about the fact that it is such a young field. Kind of as people define it right now, it's only like 10 years old. As you look back on the history of soft robotics, there's things from the 80s, there's things from the 50s that we would now fold into this field, but it hasn't been a field that we would call it such until quite recently. So I think a lot of the finding the application space for it right now is driven by finding an application where we know that the constraints that we have are still functional. So when we talk about like gait training, the easier to market thing may be that you're building a gait training rig that gets used in a physical therapist's office. Yeah. Rather than one that is like totally out in the field. So you have these like parallel discussions between like what might be able to be commercialized in the near future and like where we can see gains right away. And then you also have like the blue sky side where people need to make like really big assumptions about what will be possible in the future and then do the incremental work to get there. Because there are tons and tons of possibilities, but you have to do kind of all that nitty gritty short term, maybe we're still tethered steps. And I think that, there aren't that many robotic systems that are like human walking systems that are untethered now either. It's the tethering question is a question that we still have for some realms of traditional robotics too.
Yeah. I worked on an exoskeleton that was hard, and we did get it untethered, but it was non-trivial. Let's go with that. Mm-hmm. And it had to carry its own weight. So yes, that is certainly a big consideration when you're doing that sort of thing.
Yeah. So I think in soft robotics, it's that you're tying all of these like new problems to an already non-trivial problem.
Yes. Everything gets more complex as time goes by because that's what we do. Mm-hmm. But so making candy robots, this seems like a hard problem, and yet now you're just going to use some gelatin?
Okay. So the story about the soft robotics, candy soft robotics, is that I have not traditionally worked in silicone a lot, but my collaborator, Matthew Borgatti at Super Releaser, he has a lot of deep expertise in silicone casting, and some of his popular work, including the Glaucus, which is a single cast piece of silicone with two lines in that can walk as a quadruped. So he and I have worked on kind of more simple silicone robots together, and he's been teaching me about his area of expertise. And during one of our conversations, because we're writing a book right now, we're co-writing a book. He's going to write 8 chapters and I'm going to write 4, and we're working on the projects together. It's came up like, how are we going to structure this? Like, what are we going to demonstrate? So we were coming up with different projects that demonstrate like some foundational piece of soft robotics. And during the discussion, it came to mind to me that I was like, oh, silicone is a lot like gummy. Like, it feels a lot like gelatin-based things. So wouldn't it be really great if we made a candy robot? And then I was like, oh, I don't know.
Okay, at the time, were you eating gummy bears? I
may have been. I really like candy. Okay. But yeah, and so I was like, well, maybe we should make a candy robot. And then I was like, but it doesn't really meet our agenda. We already have these silicone robots that we're putting in the book. And he was like, no, part of the agenda is to be awesome. And so that's how I got put on the path of actually following up on the crazy idea of making robots out of candy.
Making robots out of candy. I feel like that should be the show title, even though that's way on the nose for us. Yeah. Okay. So yeah, candy. It's like Jello shot robots. Tell me more about
Jello shot robots.
That is an excellent idea. So I will totally consider that.
I can see how there are some similarities between silicone, the molding materials, and gummy bears. They have the elasticity, and they have I want to say the lack of denseness, the squishability. But you're not making the gummy bears dance, are you? Have you considered that? Sorry.
So the way that I like to work on problems is that because it is so much of the process is materials driven for me. I think that has a lot to do with the fact that I've worked in lots and lots of different materials over my careers, and you really hit this place where if you choose an inappropriate material to build something, it never works right. And you're fighting it the whole process. And so for me, when I wanted to tackle the problem of making a candy robot, for me, it was very process driven. So the process that I like to think about when working on emerging technology, it starts with why. And so in the case of candy soft robots, the why was as an art project. I really, really love edible art. I think that people talk a lot about interactive art, and I can't think of anything that's more interactive than food because it engages all 5 senses and then it becomes a part of you. Like, I literally can't think of something more interactive than that. And then the other reason was like the practical why, which was we could put this in a book. And then the other why is that like it's delightful. Like, it's delightful and or disgusting, and like both of these are strong emotions. And like if you're going to make something, making something that elicits a very human response is appealing to me. As I move then through the next stage of what I want to do when working in an emerging field is that I want to talk to experts. And for candy robots, I was like, there aren't any experts. There, it's new as a field. I'm putting air quotes around things that you can't really see. And so the thing about this was like, well, who are the experts? I was like a food scientist, a soft roboticist. I ended up speaking to a chemist for a good long time, a person I know who's an extreme candy enthusiast. She's eaten every mass-produced candy in North America, as far as I can tell. So I talked to all of these people and was like, okay, great. Like, let's talk about what this means. Like, let's build out my understanding of candy generally and like soft robotics with kind of a more focus when we're narrowing in on making a candy robot. And then after that, I defined the specs. And so in this case, some of my specs were like, it can't be only technically edible. So people were like, well, you can eat string. And I was like, no, we're not going to make a robot where we're going to eat string, even though, yes, technically it's edible. Another was that I wanted it to, again, like either bring joy or disgust. That was another one. One was that I had seen some various edible art projects that were like edible electronics where you essentially had to eat around the wires. And I was like, I don't really think that achieves my like aesthetic goal if you have to eat around something. So for that, then I was like, you have to be able to eat up to where it joins to the computer control. So I wanted to, for example, if I do a pneumatic system, wanted to use airtight tubing that was also edible. And so then once I have the specs in place, I start a materials exploration. I look at all of the materials that seem like they might fit the problem space, and I start playing with them. So in this case, I started both with making homemade candy, and I started with store-bought candy. I did both paths simultaneously. And I did a bunch of materials exploration where I just tried to find out what are the characteristics of these materials, and then could I apply them to this problem or not. So I looked at licorices. I didn't limit myself away from the idea of a hybrid robot, a robot that has soft and hard components together. So I looked at like drilling out holes in sweet tarts. I looked at fruit leather, like is fruit leather airtight? I made many different recipes of gummies. And I also, so I went on this kind of big, broad exploration of all different candies that I could apply to the problem. And then once I get through doing the materials exploration, I see what's promising and what's not promising. Like a lot of the candies I bought, ultimately I was like, okay, now I'm going to give these away, and I'm going to be the person who gives lots of candy to people. And that's also a nice
Halloween
side
every day.
effect. It is Halloween every day, especially when I got in a time crunch, and I was like, I'm just going to order a case of Nerds Rope. And so I gave a lot of Nerds Rope. But so anyway, that's kind of the stage I am at right now. Like, I'm built out one simple actuator that was like multiple kinds of licorice, which actually made me laugh because people who hate licorice was like, you have gone into the technically edible zone.
Oh.
They were like, black licorice is not food. And I was like, oh, I really like black licorice.
Okay, so I want to, this licorice thing, I saw it on your video. You gave a talk and you had it, and it was a red vine on the outside, so a hollow licorice, which could make excellent tubing as well. And then a solid black licorice vine that was not hollow, solid. And then you threaded the black licorice through the red licorice, and it bent. I don't remember how it bent.
It had little voids cut out of the red vine, and so because it's flexible, it's wherever you don't have.
Oh, you cut out vents. Yes. Okay. Yes. And then when you pull, so did the black licorice? It was connected, or it couldn't retract through the hollow licorice?
So as you pull on the black licorice, it was a spiral piece of black licorice. So I left the spiral end to be the portion where that's the anchor point for the pull. And so as you pull the black licorice cable, the red licorice, where the vents are, that's where it bends. And then it slides back. And that was funny too, because then I started exploring edible lubricants for candy. Because I wanted them to slide nicely. Then
almond oil and olive oil would be pretty good, that's hydrophobic, so it shouldn't get in with the candy, with the sugar.
I had that theory too, but essentially oil also works as a solvent on sugar. So that was something that happened. And then I talked to a food scientist about it a little bit, and he was like, pretty much most liquids that sugar dissolves so easily, it's a property of sugar itself that almost anything liquid would cause the sugar to become gummy or melt. And so I had to switch to dry lubricants only.
Such as crushed up sweet tarts?
Such as, I was using cornstarches, powder sugars. Someone suggested that I should use the sour powder. That might be really
citric
delicious.
Acid, yeah.
Citric or acetic, or one of the acids.
Citric.
Yeah, there's like 10 different interchangeable edible sour acids that you can buy if you go to the molecular gastronomy stores.
Okay, and then the other thing I saw in the video was you were talking about fruit leathers, which is, fruit roll-ups, really common, pounded fruit into jam and then dehydrated so that they're flexible. They're not particularly durable, but you can definitely make a bladder with it and connect the edges, either using a sugar syrup or sometimes just licking them. You can create little pockets. And I know that because I have made the pockets and then filled the pockets with other things. But since we were talking about soft robotics, you could make like the inchworm sort of thing if you made a pocket and could pump the air in and out. Have you tried that?
I made essentially what looks like kind of a heart. So since I only got through the materials exploration, what I wanted to test was whether or not I could seal it and it would work like an airtight film. And the answer was yes. I made like this thing that kind of looks like a heart because when you pump the air in, it expands and then it contracts again. Yeah, I think that the thing about going down this materials exploration path is that it's really provides the answers to what I might want to make. I didn't want to start where like I already pre-designed what the robot was going to look like or what the robot's function would be or what it would move, because I can come up with a better idea once I know how the material behaves. And so the question that I have for myself about, like, now that I'm on this path and I'm making all of these things is, okay, now which of these is like the most fruitful? And so that's kind of, again, talking about the process of fruitful.
Pun intended.
And then so now that I have all of these things that I've tried, now say like, what do the trade-offs? So what are the trade-offs of going with a fruit leather versus a gummy versus like even the trade-off for like the most delicious gummy versus the most functional robot gummy is like an interesting question for me too, because I'm writing a project-based book with someone. So I need to make sure that the project is easily reproducible. So that's another one of my specs. You talked about durability, and that was something that in my specs, I don't want the robot to be durable. I think that actually when working with food, making something that lasts a long time is actually not a desirable trait.
Well, no, but they should be able to actuate it 5 times. It shouldn't be one thing and then it disintegrates. That's not as much fun.
Yes. So my spec was that for that was like, you need to be able to make it the day before you want to present it. So it needs to be durable enough from like a static standpoint to last 24 hours, because I don't want to put anyone in a situation where like you have an expectant room of people who want to eat your robot and you're like frantically trying to make it and then it fails and then you've had
We've all been there.
Fail. Yeah.
the demo never works on the day of the demo.
Exactly. So I wanted it to be that you could make it the day before, and then for you to be able to actuate it, like, you know, maybe half an hour would be ideal. Like, we'll see what the trade-off is. Like, maybe I can come up with something delightful, but you can only cycle it for 15 minutes. It probably would be fine for like this particular application. But I didn't want the spec to be that it lasted a long time, because like nobody wants old and dirty food that's been actuated everywhere. And like you kind of lose your opportunity too if no one gets to eat it at the end. So if it's so durable that it becomes so precious that no one will ever eat it, then I think that's a missed opportunity.
And yet I want to make little gummy worms that crawl across the table, and I'll just sit on the floor and look up with my mouth open and they'll crawl into my mouth. And it will be horrible. And Christopher's face once again. I wish you all could see the look on his face about how horrible this sounds to him, but I am jazzed.
Oh, so yes, definitely crawling into so things that have come up when, that's the other thing that's really wonderful about this project is that people are really eager to talk about it. So definitely in the disgusting side, some of the things were like eyeballs that pop out of something hard, or like there's a Klingon dish in Star Trek where it's like a plate of squirmy things. And they're like, oh, can you make that? And I was like, actually, that's probably not a very hard problem. Like of things that we could do with it, making a plate that kind of wiggles in an indistinct way might not be a hard problem compared to some other things. Another one was like a snot-based thing. Like if you had like snot coming out of a nose, but was actuated, kind of on the disgust side. And then kind of on the delight side, you had said like dancing gummy bears. Like that is a delightful kind of interaction. And like both are interesting.
How are you, so assuming pneumatics, how are you going to, how do pneumatics work at all? I mean, I know how a pneumatic drill works, but we're not talking about that level of, or a pneumatic hammer. That's the word, right?
Jackhammer.
Sure. I know I can go to Home Depot and get this giant loud thing that will make compressed air. But I don't want that for my party of dancing gummy bears. How do you make something small that will do what you want it to do? Or is this a bike pump?
So a lot of times when prototyping, we'll use like a sphygmomanometer. It's the like little bulb, that's the part of the air.
Like a turkey baster?
Yeah, like a turkey baster. So the one I was thinking of and the one that I use is for blood pressure. Yes, and so it's a little bulb pump, and you have cable. You have tubing that you connect to that, but also you have used compressed air a lot. So the compressed air that's for beer making.
Oh, okay.
They make little cartridges, so you can hook that up to like some little valve systems, or you can do it. So it just depends. A lot of my prototyping I will do with a hand pump, though, just because you want to be able to iterate quickly. And since I don't have a specialty in electronics or code, I often will collaborate with someone who that is more their area of expertise, and I will handle more of the like soft goods and embodied complexity side.
How much does puppetry and the ability to make interesting joins with fabric that do non-obvious things apply to soft robotics?
At least the scale of robots that I work on, which is kind of this small size to like human wearable stuff. Yes, I think that the fact that I have worked on costumes and on puppets is the entire way I have for visualizing these systems. So I know a lot about human factors, and I have also worked with lots and lots of different materials and kind of learned tricks of the trade for motion, and now can apply this just to a new space.
I have a small hand puppet and I really like it. Christopher still doesn't know why I got it, which is fine because I don't know why I got it, but it's sort of a not well built frog. And I had to play with it for a long time to realize what expressions I could get because of the way it's built. There's some fixed things about it. And I suspect those are design choices from the puppet makers, puppeteers,
puppetologists.
God, that's a terrible word.
I usually say puppet builders or puppet designers.
It was the puppet.
Puppetographers.
I can't get this. Sorry. Yes. So, I mean, this is also an origami problem in some ways, that you have a fixed surface and you want to be able to move it in certain ways. And you mentioned vents as one way that allows things to move in one direction. How do you learn this stuff? I mean, I play with origami, but even as I thought about robotics, I was like, I don't know how to get from here to there with the origami. And I was looking at hard robotics, little tiny actuators. How do you learn this stuff?
I think that at least in these kinds of problems, it's that everyone is bringing all of the things they've already done. So you'll have a toolkit of all of your knowledge base, and then you are finding a collaborator, or you're collaborating with different parts of yourself even to say like, okay, I know this from this and this from this. Like, what happens if I blend these two pieces of knowledge? And then that's how you make something novel. So for me, yes. Because I have worked on the costume problems and the puppet problems and the spacesuit problems, like I have a very deep toolkit for physical prototyping and materials understanding. And so I'm just like, once I have a new problem, I'm sifting through all of the things I've experienced before and say like, this looks like this. Like maybe no one else would make this connection, but like, let me figure out of all of the things I've tried before, which ones speak to this problem. And then if I look through my toolkit and I don't have anything, then the next step is that question of then who is the person I talk to? Who does have the tools that I need to get this done?
That's totally fair. But I was more going to if I wanted to start, where do I even start? Is this learn to sew and learn to make puppets, and then that will get me further into soft robotics? Is this understand silicone better and start making more Jell-O in my kitchen?
It depends. Again, it depends on what kind of robot you're interested in. If you were interested in silicone, so I just taught a bunch of students about casting silicone, and they had these questions. They said, "Okay, so you taught us how to cast silicone. We made one actuator together. Now, how do I do more?" And I said, "Okay, well, probably what you're going to want to do is one, cast more silicone things because you will need stronger skills in order to reproduce your work and to get the outcomes you want." So that's one phase of it. The other phase of it is that there's an existing body of work. So look at all of if you want to work in silicone now, look at all of the silicone soft robots that exist and say like, okay, what design patterns are people using that are working well? So some of them are shapes that you learn the shapes from this library that people are unintentionally creating by making all of these soft robots. And then you look at thickness. So some areas are silicone thick for the stability, and some of them are thin. Some people put fabric inside for constraining things. Some people are wrapping things around the outside to change the way they inflate. Like some people are making them like Mckibben muscles. So you're like, okay, so this is now a library of ideas by looking at what other people have already done. And then also, then maybe you're wanting to look at this bio-inspired space. You're just like, I want to make something totally new. If I look at the natural world and the majority of things are soft or soft and hard together, is there something that is really interesting to me that I can simplify to the point where I can actually make something that approximates part of its function? And then you try, and then you make one and it fails, and then you make one and it fails, and then you iterate until it works, and then you've discovered something. I guess
you're telling me there are no shortcuts, and I'm going to have to actually learn something and try it out?
Yeah, I guess the thing is too. I guess maybe the answer is there are no shortcuts. But I guess the thing for me is that it's also not a mystery. Like it's a process, but
yes,
you can learn the process. And also, I guess one of the steps that I forgot is that when looking at the silicone problem, I think people get really narrow in where they want to look for ideas. So they'll say, like, I looked at all of the silicone soft robots coming out of universities. And I said, well, did you look at all of the special effects artists? Because they have done all kinds of things that are totally different than the things that are being done in universities. And so if you bridge those two domains, are you going to come up with something that's like even more interesting and more exciting?
Yes, I do enjoy breadth of knowledge. I mean, that's why I read about octopus intelligence and musculature, because who knows when I'll need that. So yes, I do agree that the cross-pollination can lead us in really interesting places. One of the things that if someone is listening and they want to try out, you mentioned a book, which I want to ask you a little bit more about. But before that, there's Glaucus. And you also mentioned this. It's from Super Releaser. And is it your collaborator who's on the video?
Yeah, Matthew Borgatti. He started Super Releaser by himself, and then was working on these problems, and at a certain point had asked me, like, what next step should I take? And I said, I think that maybe you need a partner. And I didn't mean myself. And my husband said to me, so, and then you said, and you should pick me. And I said, no, I didn't say that at all. That hadn't occurred to me. But it was funny. Then I went back to Matt and he said, oh, no, that's what I thought you meant. So I guess I unintentionally put myself on this path. But no, Matthew has been working on soft robotics actually a lot longer than me. He's worked on it for going on 6 years now. And he developed Glaucus before we started working together. And it's a very unique quadruped like I said, it's a single cast piece of silicone. So it's a one-part actuator, which is kind of amazing for a quadruped walking robot.
And people can download the mold for this from Thingiverse and then use silicon to build it, to do the mold, and then hook up the little, what do you call them? Spire?
Phenomenon. Damn it.
The little bulbs, the little air bulbs.
Sphygmomanometers. That one always gets stuck in my craw. Sphygmomanometers, I think is the right way.
The turkey baster thingies.
Yes.
And then they can have a little robot that will walk across the table. I mean, assuming this all goes perfectly the first time or the seventh time, however long they spend on it. But it's all theoretically someone could go out and get all the parts.
Yes, theoretically someone can make this. In reality, we have had one person recreate the work. She was a university student in Korea, and she actually came to our lab and brought her Glaucus with her, which was fantastic.
Oh, that's so exciting.
The thing about the Glaucus, though, is that because Matthew is an expert in silicone casting and does that at extremely high level, it is actually very difficult for other people to reproduce. So what we are working on right now is a book that is for Make Media. We're not sure when it will come out. We're still in the process of writing it and writing projects. But the goal for us in this one was to simplify, to make projects that were much more achievable and repeatable. And so that is very exciting. So, for example, I had put out that I wanted to come up with a soft robot that we could cast in not a custom mold entirely. So you'd only have to 3D print one small part. And then the rest you could use off-the-shelf parts to make the molds. So you can cast it now in a PVC pipe. And so that robot I had 16 people make last week. And I think we had 15 successes. And we took 2 hours to make them. So that's kind of what we're working on for the book, to make this a lot more accessible. But for people who want to start working in soft robotics, in terms of the silicone cast robots, there's quite a few small projects that you can find on Instructables, or Aidan Leach is our intern, and he goes by XYZ Aidan online. And so he has done a lot of simple work that people reproduce. And it's pretty fantastic to see kind of how the community of DIY soft robotics is growing, in addition to the academic and the military pieces.
Sure. I mean, being able to do it at home and to think about it and then go out and apply it to our careers, I mean, that's one of the reasons a lot of people are into the maker movement, is just that thing you wouldn't even get to try at work until you're good enough. You can say, oh, no, this will work. I'm sure of it. Mm-hmm. So you mentioned that you don't do a lot of software. You don't do the control system. Does your partner do the control system?
He does some control systems, but I think long-term we have found that more of the people we work with have expertise in that area in terms of clients and potential collaborators, whereas fewer people have kind of this fabrication plus design base to do the soft component side. So we thus far have been putting more of our eggs in that basket. But we started working with someone who is a postdoc at Yale doing she's doing cosmology, actually, but she also is interested in doing science on physical things. And so she is one of the people we've been talking about starting to do more robust analysis of kind of the underpinnings of the physical work that we're doing. So we're definitely interested in collaborating with people who kind of either the electronics and coding side is their specialty, or people who are interested in the simulation side of the problem. So simulation is something that is in the process of being built up around these nonlinear systems. And so I think that it's really interesting to us to hopefully long-term meet people who are working on that side of the problem as well, and kind of add that to the set of tools that we're applying to the space.
Oh, I bet. And it is so nonlinear that simulations will improve a great many things. And since it is non-trivial to construct, a simulation is very good. I'm just going to go with that. Stop babbling on. And yet I'm sitting here thinking about the control loops you'd use and what feedback you might get, what sensors you could put in to make sure you weren't damaging. All right, I'm going to go off and not bother you with this, Kari.
Oh, no, I want you to bother me with this as much as possible. But we also don't have to make the audience privy to that part of the audience, the conversation, unless you're interested in that.
No, I think we have kept you for long enough for a beautiful weekend day. Christopher, do you have any questions before we go?
So many questions.
So many questions.
No, I don't think, at the risk of starting a whole other discussion, I think we should probably.
I mean, yeah, I guess the thing is that we barely scraped the surface of the potential things to talk about, but as long as you guys feel like you got what you needed.
I mean, it is fascinating to me because it does seem like a really very early days of something that almost shouldn't be, but it's kind of amazing that there's this whole field it's very untapped, right? I mean, people are just kind of learning the principles and discovering and making the principles, I guess.
I am in the process of reading all of the Soft Robotics journal. So it's Soft Robotics is the name of the journal, and it's the academic journal that is entirely devoted to soft robots. And it is to the point where there are only 120 articles. So
yeah. I
can literally read the entire primary source for this work. Obviously, there's some very high-profile work that's going into like Science and Nature and other like big-name journals as well. So it won't be the whole field, but even to say like, okay, I can read 120 articles and have read the bulk of the papers is kind of amazing.
And then you'll write a book so that other people can get involved. I think that's pretty cool.
Excellent.
Kari, do you have any thoughts you'd like to leave us with?
I think the reason why that I'm really drawn to soft robotics as a field is that, for me, the most exciting space to work and the best problems to solve are the ones that are entirely novel and the ones that can't be solved by a single person. So I just have this passion for thinking across domains and being like, what if we mix this and this? And what if I get to have a conversation with someone who knows everything about something I've never even heard of before? And how exciting is that space? And so I feel like this kind of play plus rigor is a space that there's not enough time for in some domains, and that I feel like the best problems are the problems that require this kind of combination of ideas plus rigor. And I just really want to encourage other people to get excited about these in-between spaces.
You have certainly made it sound very appealing. I am pretty excited about soft robotics now. So yes, and I totally agree. This is fun and it's going to be great. I look forward to your book. So as soon as you have it out or have a release date, I will be asking you for information on that so people can get it. Thank you so much for being with us, Kari.
Thank you so much for having me.
Our guest has been Kari Love, soft robotics collaborator at Super Releaser. There were some other titles in there, but we'll stick with that one. Links to everything will be in the show notes. You know, the notes that live in your podcast app, but also on the embedded.fm, where there is also a blog, a contact link, assorted other goodies, and a new search bar. Thank you to Christopher for producing and co-hosting. And of course, thank you for listening. I have a thought to leave you with this week from W.B. Yeats. I have spread my dreams under your feet. Tread softly, because you tread on my dreams. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.